You've made it to the last video in Chapter 10, Structure of Solids. Now a little disclaimer here before you get your undies in a bundle and get real excited. Solids is not going to be one of the most important topics that I would spend time on when studying for the AP test. You might find maybe one multiple choice question that deals with structure of solids. So it's good to go through this because, again, that one question could be a big deal in the end. But you don't need to know more than what's in this study guide when it comes to solids. So first of all, we're going to classify solids in one of two categories, crystalline or amorphous. And you can kind of guess what this would refer to then, the structure of the particles. In a crystalline solid, the particles are very organized. They're in a rigid, like crystal structure. This would be something like ionic compounds, where it's an organized pattern of oppositely charged ions. They tend to be hard and brittle and have very high melting points. An amorphous solid, on the other hand, would have these particles in a disorganized arrangement. You got a bunch of particles, they're just kind of randomly scattered close to each other. There's not an organized pattern, an irregular, disordered arrangement of particles. And again, this could be lots of covalent solids like waxes and plastics and glasses. They tend to be softer and then have a little bit lower melting points because there isn't this rigid, organized pattern of, especially in an ionic solid, like an oppositely charged ions. So let's look at these ionic solids. It's probably the best example of a crystalline solid, and some of this is going to be familiar to you. We'd mentioned that these ionic solids have an alternating pattern of positive and negative ions. So here might be an example of a sodium chloride crystal. Now, when we write ionic formulas, often we call it like the lowest repeating crystal pattern. So that's why in an ionic formula we try to simplify the ratio to like the simplest whole number ratio. So I would never report an ionic formula with a ratio that might be like, oh, I don't know, something like Cu2O2. We would simplify that and just put CuO because that would be the simplest repeating pattern of the crystal. Now that's a little different with the covalent compounds because then they exist as these large molecules. So you could have a covalent compound that might have like a 2-to-2 ratio of atoms or a 4-to-10 ratio. And then we don't simplify because that's the true structure of the molecule. But in an ionic solid, you don't necessarily have individual molecules. You just have a repeating pattern of oppositely charged ions. These strong electrostatic attractions are what give us these really high melting and boiling points in ionic solids. Like I think salt has a melting point of like, I don't know, 800 degrees Celsius or something crazy like that. It's nearly impossible to melt sodium chloride in our lab, although every year kids try. But it's because of these strong attractive forces between the ions, even stronger than like hydrogen bonding. Here's another word that might ring a bell. Coulombic attractions. Ionic solids have low vapor pressures due to those strong Coulombic attractions within the crystal structure. And again, that just kind of refers to the attraction of the oppositely charged ions. Ionic solids are usually brittle. I'll make note of that. And again, that's because you've got this rigid pattern of ions in the crystal structure. The solids do not conduct electricity. In the solid phase, we do not conduct electricity. In order to conduct electricity, you need moving charged particles. Well, an ionic solid is very rigid. Those ions aren't moving. So if you want to get the ions moving, you have a few options. You could melt the solid, and then you're kind of breaking down that rigid crystal structure a little bit. Or the most common option, dissolve it in water. When the ionic compound is dissolved in water, those ions dissociate. And then you've got these free moving ions in the water, and that should conduct an electrical current. Alright, so going back to this idea of Coulomb's law, here's kind of what lets us compare attractive forces between different ionic solids. And we kind of mentioned that you're never going to have to do calculations with this equation, but it does kind of explain properties of different ionic compounds. Lattice energy is defined as the energy released when an ionic compound forms from its gaseous ions. And the two things that we're looking at when we compare lattice energies are the charges of the ions. So if I had something like, magnesium oxide, those charges are +2, -2. Versus something like sodium chloride, where the charges are +1, -1. Number one factor that affects the strength of these ionic attractions is the charge. So the ion charges +2, -2 is going to be a stronger attractive force than a +1, -1. The second factor that we may look at would be the distance between the ion centers, and that kind of refers to the radius of those ions. And so we can just get this by looking at the periodic table and comparing trends in radius. So if I had two compounds that were both like +2, -2, so maybe my other compound was something like calcium oxide, same charges, the stronger attractive force is going to be between smaller ions, where those nuclei are closer to the electrons. So if I'm dividing by a smaller R value, that should give me a larger lattice energy, which is technically defined as energy released when the compound forms. But on the flip side, that's the amount of energy you'd have to add to break apart the ions. It says for ions of a given charge, the smaller the ions, and thus the smaller the distance between the ion centers, the stronger the Coulombic force of attraction, and thus the higher the melting point. So I think we referred to this earlier, that indirectly they might ask you a question like A, B, C, D, which of the following ionic compounds will have the highest melting point? Well, I kind of want to refer to this equation. I want the strongest charges, the highest charges, or I want to look for the smaller radii. Another type of solid that we want to look at are molecular solids. And now obviously if I see that this is a molecular solid, I'm thinking that these solids are composed of molecules, individual molecules. And that makes me think covalent compounds. Covalent compounds exist as separate molecules. They're attracted to each other by intermolecular forces. So a little different than the ionics, where the ionics are just these repeating positively and negatively charged ions. So here we're going to have like covalent compounds. Examples they're giving me are like water, ice, dry ice, carbon dioxide, usually non-metals, since we're talking covalent compounds. We could mark that in. These compounds should be made of non-metals. A real common non-metal that you'll see in these molecular solids might be like carbon family, like the carbon dioxide, where you can get lots of tetrahedral structures that can be kind of attracted to each other through intermolecular forces. Obviously then, since there are no ions, these molecular solids are not expected to conduct electricity. They generally have lower melting and boiling points, because again, now these intermolecular attractions, like dipole forces and hydrogen bonds, these are weaker than attractive forces between ions. The ionic compounds have the high melting points. These are generally a little lower. And again, good examples, carbon compounds that might form these large macromolecules or polymers, especially like biological molecules, like all the molecules that are attracted to each other in DNA structures would all be considered molecular solids. Another group of solids are called networks. Now again, network solids are going to be covalently bonded atoms. Covalently bonded atoms. I like making note of this. Great examples are like different forms of just carbon. It's like graphite, diamond, or silicates. So this commonly occurs with elements from the carbon family, like silicon, or again, carbon. Carbon can do a couple different things. These tetrahedrons could arrange themselves in a little bit more of a crystal pattern, and then we get diamond. Or they can arrange themselves in these layers, and then that's graphite. And those arrangements change the properties. So obviously graphite is a lot softer than diamond. That tetrahedral repeating pattern of carbon tetrahedrons, that's really strong and rigid, which is kind of what they tell me here. These covalent network solids generally have higher melting points. They're rigid and hard because of those angles, the tetrahedral angles. Now, graphite still has a high melting point. It's a bunch of carbon atoms, but because of the arrangement, it's a little bit softer. Obviously, like pencil lead or graphite is softer than diamond. So again, I kind of think for network solids, I think of it as a network of a particular atom, especially carbon and silicon. Those are probably some of the best examples of network solids. So they're covalently bonded atoms, but not the same as covalently bonded molecules. Okay, now along those same lines, we mentioned silicon. Silicon is a good semiconductor. Because of this, we can dope silicon with different elements, and it can change the properties. So here, silicon is this metalloid, where it has properties similar to a metal and a non-metal. It's kind of in this gray area of the periodic table. There's a couple different ways we can dope silicon and change its properties. So let's say I got silicon with 4 valence electrons. One option is called an N-type semiconductor. If we dope silicon, which means like we mix silicon atoms with an element carrying more valence electrons, we call it an N-type semiconductor. So for example, let's say we dope this silicon, we mix it with, like what's listed here, arsenic. And I look arsenic up on the periodic table, and I find 5 valence electrons. If I mix the silicon with an element that has more electrons, I'll show an increase in conductivity. So it's almost like we can make the silicon act a little bit more like a metal, but depending on how much arsenic we add, we can get like a specific amount of electrical conductivity. Pretty wild, huh? Now, people always get these mixed up, this N-type semiconductor. Think of it this way. N-type makes me think negative. Negative charge. You've mixed the silicone with something that has more valence electrons. there's more valence electrons. If this other element has more valence electrons, more electrons should create kind of a negatively charged situation. So I always remember that. The N-type semiconductor will have the original element, often silicon, mixed with an element with more valence electrons to create a negative charge. On the flip side, we could also mix the silicon with an element that has less valence electrons. So what if I went one group over and had like boron with 3 valence electrons? So now this would decrease the electrical conductivity of the original silicon. It's not listed here, but we'll write this in. It's called a P-type semiconductor. P-type. And I bet you see where the P comes from. P stands for positive. A positive charge. This is a situation where I have less electrons. So if there's a lack of electrons, it creates a situation that's more positively charged. So I'd be familiar with this concept of a semiconductor where I have this silicon, this metalloid, and I can mix the silicon with elements that either have more or less valence electrons to alter the exact electrical conductivity. If the element has more valence electrons, we call it N-type, because there's overall a negative charge. If there are less valence electrons, we call it a P-type, because there would be a situation that has a positive charge. And here's our last option for solids. I mean, this is just driving you wild, isn't it? Metallic bonding. Sometimes I don't even think of this as bonding, but I do picture metals as having what we call a sea of electrons. So here's the deal. In a metal solid, a pure metal, you've got these positive nuclei, and the electrons are kind of delocalized. The electrons are kind of free to move about all the positive nuclei. And so that's why this term sea of electrons is used to describe the atomic structure within a metal solid. A bunch of delocalized electrons that are free to move. If you have electrons that are free to move, bingo, you've got conductors. That's why metals are such great conductors. That's why metals are malleable and ductile. Because you don't necessarily have a rigid structure here. Since those electrons can kind of move and flow around the nuclei, we can kind of change the structure of the metal. Now, another thing that we should mention in terms of metals, again, kind of has to do with this idea of mixing atoms of different metals to form what we call alloys. Alloys are mixtures of metals, and often we'll see properties that kind of take into consideration the different metals that we're mixing.
Heidi Brooks, style 6540, Heidi Brooks, 6540.
Excellent. There are two options, two different kinds of alloys that we should be familiar with. One of them is called an interstitial alloy. In an interstitial alloy, you've got your typical atoms of a particular metal, and there's a smaller atom that kind of tucks itself into the spaces between those original metal atoms. Those are called interstitial spaces, the space between the atoms. So this would be a small atom, such as carbon, that would kind of fit itself in between the iron atoms and fill in those little spaces between the iron atoms. Now, if I don't have as much space between the atoms, so there's not as much space for the electrons to move, this typically creates a metal that's more rigid and has a decrease in malleability and ductility. So again, it's a more rigid structure. There's not as much room for these electrons to move. So that's called an interstitial alloy. The spaces in between the atoms are called interstitial spaces. So it kind of makes sense. It's when a smaller atom is mixed with the original metal to fill those spaces and cause the metal to be more rigid. The other option is called a substitutional alloy. And again, this kind of makes sense. Now I'm going to mix metals that have about the same radius, where we really do just like substitute one metal for another metal within the same lattice structure. So the electrons are free to move around all these nuclei, the zinc nuclei, the copper nuclei. Brass is a good example. The copper and the zinc have similar radii. And then our final product is a metal that has kind of properties of both elements. The density typically lies somewhere between copper and zinc. The conductivity would be kind of between copper and zinc. So again, this is called a substitutional alloy, where you're mixing different metals, all metals, that have about the same radius. And now the properties that we see are kind of a combination of the properties of the metals that have been mixed together.